In this video, I'm gonna be talking about another important article in zero-shot learning, but now we are in the task of entity linking, and we are using a proxy-based approach because the paradigm of retrieval and then re-ranking is very challenging. So in the retrieval, you will see how we will deal with these complexities to have a better approach for this entity linking problem. So this is our task. This is an article in 2022, and the motivation is that a recent advancement in the domain of biomedical entity linking is a development of powerful two-stage algorithm. We have candidate retrieval stage that generates just a short list of entities for each mention, and then we have candidate ranking. So first we have retrieval, and then now we have top K candidate, and now we are ready to do those re-ranking algorithm because this data until here is very noisy, so we should re-rank it. So this is a paradigm that first we do retrieving and then re-ranking. But retrieving, even at this stage, we still miss lots of important entities. And so it's a very delicate process. And the idea is that we show that pairing a proxy-based metric learning loss with adversarial regularizer provides an efficient alternative to hard negative sampling. So it's an alternative to hard negative sampling in the candidate retrieval stage, in the first stage. And then we show that they have competitive recall metric and so on. So they propose and evaluate a novel loss for the candidate retrieval model, which breaks the dependency between the positive and negative pairs. So the contribution is that a novel loss which significantly outperforms the benchmark cross-entropy loss on the candidate retrieval task when using random negative, and performed competitively when using hard negative. And they design and apply an adversarial regularization method based on this first gradient sign method. Goodfellow was the inventor of GANs. Everybody knows him. And so the proxy-based method is that state-of-the-art entity linking methods such as Blink leverage metric learning loss during training to make mentions similar to its assigned entity representation. However, training them can be highly computationally expensive, but these proxy-based losses are significantly less computationally complex. So for what we mean by adversarial regularization is that for the entity linking systems, they often rely on careful mining of hard negatives to boost their performance at the expense of increased computational complexity. But this article is trying to use an alternative approach. A potential alternative to hard negative mining is training on adversarial examples. And so we have entity linking task. Each document has a set of mentions. These are mentions. And the task is to link each mention to an entity where each entity belongs to the knowledge base. So in this work, we focus specifically on the problem of biomedical zero-shot entity linking, and because we are assuming that we are doing zero-shot, so there is no intersection between your training and test data. I will focus on specifically on the candidate retrieval task, where the goal is given as mention M sub I, and will reduce the pool of potential candidate entities from a knowledge base to a smaller subset. So this is an overview of proxy-based entity linking, and you see that the mention and entity embeddings are encoded into a joint embedding space. And during training, magnitude of the gradients of the proxy loss with respect to the embedding is a function of similarity between the mention and the entities. So the proxies, I mean those entities. And the gradients are represented by arrow whose indicate the magnitude. And so the loss is that we have given a set of data points corresponding to mention representation. So we have this mention, and we have a set of those proxies, those entities corresponding to E. And now the categorical loss, this is a categorical loss, could be defined like this, that we want to maximize this similarity between mention and entity. And we use, and E plus is just the positive proxy. We call it in the machine learning literature, we say positive samples. And the same thing for negative samples or negative proxies. It's a set of negative proxies, and so we have positive and negative proxies. Then if you just take the gradient of this categorical loss, you can take the derivative and say if it is positive, then you take this gradient. Then your gradient becomes this. But in practice, training is performed with negative sampling, and if the negatives are sampled randomly, often the exponential term for positive entity is much larger than that of negative samples, and the gradient vanishes. So when your score between your mention and your positive is very, very much than your score between your mention and your negative proxy, then this gradient vanishes, and it's a very so this behavior is desirable when training with the full distribution of negative pairs, but it's still learning in the noisier sampling setup. So drawing inspiration from the proxy-based metric learning losses we can formulate it as this. So this is proxy-based loss for candidate loss, and we use this alpha is the hyperparameter controlling how strongly positive and negative samples pull and push each other. This delta is your margin, and as I said, alpha is hyperparameter. So if this alpha and this delta are very large, the model will be strongly penalized for the positive pair being too far from each other, and conversely the negative pair for being too close to each other. And if alpha and delta are very small, I mean the other extreme, the model will receive weaker feedback. So it's a trade-off between them. And the soft plus function, a smoother approximation of your ReLU nonlinearity, introduces an additional margin beyond when the model stops penalizing both positive and negative pairs, and it reduces overfitting. The gradient of our proxy-based loss function is this, where this S plus is the score between your mention and positive proxy, and S minus is your score between your mention and negative proxy. So our regularization is based on simple adversarial training, that fast gradient sign method, and you just update your adversarial like this because you know the gradient of loss. And epsilon is just a small number defining the magnitude of the perturbation. And in the context of entity linking task, we are interested in generating examples adversarial to the learning metric. In other words, hard negatives and hard positive examples for a given mention. To this end, we applied the following perturbations to the entity encoder input embeddings of your entity. So M is the anchor mention, and we want to have the closer to our positive sample, and we want it to be very far from the negative sample. The classic paradigm in triple networks, if you're familiar with triple loss, it's the same idea. And so given n negative entities for a mention, the generated adversarial entity embeddings are used as additional training examples, giving rise to an auxiliary loss term that encourages the model to be invariant to local adversarial perturbations. So the final objective is just minimizing this. And this lambda is just a hyperparameter that controls the relative contribution of these two losses. And again, the datasets that people use for entity linking in the context of biomedical domain is either you are using med mentions or this one zeroshot linking dataset, which is just a general domain datasets. And it's from Wikias, and it has 16 independent Wikias. So the model architecture is that given a mention and its surrounding context, an entity, tau e, this is your entity, we obtain a dense vector representation, and this is the reducer, because we reduce the output of the transformer. Is like a pooling mechanism. And so we have representation of mention, we have representation of your entity, and now we use just the mean pooling, so reduce is just a kind of mean pooling. So the retrieval model is optimized with the proxy-based loss, and for hard negative mining, retrieving hard negatives requires running the model in the inference mode over the entire knowledge base. Then for each mention, the most similar, for example, the hard negative are sampled according to a scoring function. So running a forward pass over the entire knowledge base at regular intervals can be costly and time-consuming, as the knowledge base often amounts to millions of entities. Moreover, the computational complexity of retrieving hard negatives may grow exponentially depending on the scoring function. And this is the appendix that they use for. It's a very standard thing. We use this token for mention and entities, and then we have a right context, left context, because they are surrounding mention with the right and left context. Same thing for description, because we can take advantage of description of entities. So we have what is the title of that entity and what is the description. And again, we use this as a special separated to token. And because UMLS is very important in biomedical domain, and descriptions of entities you can get it from UMLS. So in this, the architecture of the models is that they use this very small layering rate, and because it's very sensitive, you should have a very small layering rate, and the input sequence length of cross encoder is more than your bi-encoder. Because bi-encoder is just for information retrieval, it could be very noisy, and the length of that is just a sequence. But for cross encoder, you have multiple of them. So 128 and then concatenate 128. So you have multiple, and the optimizer is Atom, and the number of epochs is just 5.